Dear all, wish you a very good day. Okay, in the previous lecture we had looked at fault equivalence and collapse ratio. How fault equivalence and collapse ratio can be calculated with the help of example. Now, in the present lecture we are going to look, or we are going to take the topic forward to the fault dominance. Okay, till now we have seen that there are many faults which at input and output results in an equivalent answer, and therefore due to the fault equivalence these faults are taken as singular fault and they get cancelled. Okay, in the similar way there is something known as fault dominance. So let us see what fault dominance is. Okay, according to fault dominance, if all the tests of stuck at fault, maybe stuck at 1 or 0, for F1 detects the fault F2, then fault F2 dominates fault F1. Okay, now if F2 dominates F1, then F2 can be removed and only F1 can be retained. Okay, what does it mean? Suppose I have an AND gate here to which I have applied a pattern 0 and 1, and this is stuck at 1. Okay, suppose this is my fault 1, this is stuck at 1. So what will happen if the circuit is faulty? That means if I am considering stuck at 1 fault here, then 1 will be output when there is fault and 0 will be output if there is no fault. So input 2 will be passed on. Now let me take another example. This is 0 here, this is 1 here again. This is normal, this is stuck at 1, and I have to check the output. So if this is stuck at 1, that is fault 2. So for a faulty case output is 1 and for normal case output is 0. Okay, and I1 will pass. So these two faults are not equivalent actually. Okay, and if I have taken a pattern 0 0 here and stuck at 1 is here, then what will happen? This will be 1, this will be 1 in the case of fault and 0 in the case of no fault. Okay, so 1 0 0 1 except 1 1, all patterns can be applied. So stuck in 1 faults are not equivalent, still they are assumed equivalent. So fault F3 dominates F2 or F1. Okay, so stuck at 1 fault at the output dominates stuck at 1 fault either at this input or at this input. Okay, so the 0 0 is the test for the diagram, but 0 0 is not the test for this complete circuit, so we cannot merge them. Okay, so let us see what are the dominating cases for various gates. If I have an AND gate, so stuck at 1 fault at the input is dominated by stuck at 1 fault at the output. If I have an OR gate, so stuck at 0 faults at input is dominated by stuck at 0 fault at the output. For NAND gate, stuck at 1 fault at the input are dominated by stuck at 0 fault at the output, and for NOR gate, stuck at 0 faults at the input are dominated by stuck at 1 faults at the output. So any of one can be removed because of this dominating nature. So for fault equivalence we go from input towards the output. However, for fault dominance we have to check from the output side towards the input side. Okay, so let us again take an example. Here we have 4 AND gates, 2 OR gates, and again an AND gate. Very similar, or you can say it is almost same as the first example that we did in the previous lecture. So we have to count number of lines first of all. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15 lines are there. So single line stuck at fault will be 2 and that is 30. Multiple line stuck at fault will be 3 to the power 15 minus 1. Okay, previously we have seen that its collapse ratio is 16:1, because when we are taking stuck at faults like here 1 and 0 1 and 0 1 and 0 so on for each. For AND gate stuck at zeros were cancelled, again stuck at 0 faults were cancelled for each AND gate. For OR gate stuck at 1 faults were cancelled everywhere. Okay, now because of this cancellation out of 30, 14 faults got cancelled. Okay, and we got the collapse ratio 16/30. Now using fault equivalence, what will happen, that is what we have to see. Okay, so I have circularized here all the dominating faults, which we can be seen very easily. Now for AND gate, stuck at one faults are dominating now. So this stuck at one fault, this stuck at one fault, there is a stuck at one fault here, there is a stuck at one fault here. Okay, now for this and this it cannot be, because stuck at one faults got cancelled by the OR gates fault equivalence. So only these stuck at one faults are dominating, which have been circularized, and therefore based on this 4 more faults get reduced, and as these 4 more faults get reduced, I get a new collapse ratio, that is 12/30. In this way, fault dominance helps to reduce even more faults in the circuit, and circuit can be checked with even lower number of patterns. Then comes fault simulation and testability measures. Okay, defect level is defined as 1 minus y to the power 1 minus t, where t is the fault coverage, how much faults we are able to cover, and y is the yield. Okay, yield is defined as number of good chips upon total number of chips. Now, so if we want to calculate DPM, that is defects per million, so defect level, which we have just calculated by this formula, into 10 to the power 6, that is what the defect level suggests. So there are circuit modeling and algorithm for fault simulation. These are serial fault simulation, parallel fault simulation, deductive fault simulation, and concurrent fault simulation. Okay, how are they related? We will be seeing one by one, if the syllabus coverage does allow us. Okay, so let us see. How can one generate a test pattern after fault collapsing, or equivalence and dominance is called test pattern generation. So once we have undertaken equivalence and dominance, after that patterns which are generated is through test pattern generation. The test pattern generation generate a test pattern for a given fault and is called test pattern generation. Okay, so the device which generates the test pattern, it is known as test pattern generation, TPG. Okay, generally if a circuit is quite large, TGP produces a fully automated, these machines are fully automated, their procedure is completely automated, and it is known as automatic test TPG, test pattern generator. Okay, now if a given fault is there, the automatically which the pattern can test this fault, but there is a proper algorithm for this. It is not that these test patterns are generated randomly. Okay, and this is called fault sensitization, propagation, and justification process. Okay, so if we have an different AND gates 1 to 5 here and AND gate 6 here, so what is fault sensitization? The output net of P1 is stuck at one fault. In this example, output net of P1 is stuck at one fault. Okay, so we need to drive it to 0 to verify the presence or absence of the fault. So fault propagation, effect of the fault are to be propagated to the primary output, that is output of P6 in this example. So if there is a fault here, its effect should come out and affect the output at this particular part. Okay, now so justification, determination of the value at the primary input so that the fault sensitization and fault propagation are successful. Therefore there is an ATPG, automatic test pattern generator. So what are the steps for it? It generates a random pattern, determines the output of the circuit for that random pattern as input, takes fault from the fault list and modifies the Boolean functionality of the gate whose input has the fault. The stuck at fault at the output of the gate P1 modifies the Boolean functionality of the gate P6 as I1 and I2 and I3 and I4 and I5, which is equivalent to I2 and I3 and I4 and I5. Okay, because I1 is not presently affecting the output conditions. Okay, then Determination of output of the circuit with the fault for the random pattern as the input. We will determine the output with respect to the random fault patterns. If the output of the random circuit varies from the one with the fault, then the random pattern detects the fault under consideration. So whatever pattern we have applied, if it varies with the defect, then the pattern under consideration detects the pattern. The fault is removed from the fault list. Step 3 to 6 are repeated for another fault in the list. This continues till all the faults are considered. Random processes remove maximum 90% of the fault and we use sensitization for the remaining 10% of the faults. In this way the ATPG algorithm works. Hope this was very clear to you. Okay, this is all for the present lecture. In the next lecture we will be seeing further about faults and their testings. Thank you.